Okay, let's calculate the center mass of a rigid body with uniform density. So here we're looking at this bar. This bar is supposed to be placed between 0.00 meters and 0.05 meters. So it's a half meter long bar. And the density is 1.2 kilograms per meter. I guess if it's only half a meter long, it's only got half that mass, right? That's mass per meter. So it is 0.6 kilograms in mass. And we're pretty sure the center mass is in the middle because this bar is uniform, right? So let's count. I think I have 20 blocks. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this 10th block. So right here, this is where the center mass is. It doesn't really require any calculation. So by calculating it, we'll be able to establish a method to calculate more difficult situations where the density may not be uniform, where the shape may not be as simple as a bar. It could be something else, more complicated shape. So it all starts with finding this expected answer right here in the middle. So let's put a 0 here, and this is 0.5. All right. So so far what we know about center mass calculation is this. Right, center mass from point masses. So we sum up all the point masses with their coordinates multiplied together. Then we sum up all the masses to get mass total. Right. So let's not look at this yet. But this is what we have. Right. We have point masses. Here, this is not a point mass. Right. Its extent is too large, and we talked about this in a separate video that if you have masses that are so far apart from one another, and their sizes, individual sizes, are much smaller than their distances, you can consider them as point masses. So the point mass formula works for not just point masses, but also situations where you have objects that are far away, much farther than their sizes, such as the sun with the Earth, Earth with our moon, or other situations such as if you have a cup that is meters away from another cup, for example. And this is not that situation. This is too big. So how do we do it with point mass? At least have some kind of approximation. Well, we can take the bar and divide it into small pieces. So since I have the grids, I will just subdivide the bar into 20 equal-sized pieces. These are little squares, so they're easy to visualize the little pieces that make up the bar. I'm not actually physically cutting them, I'm just marking on the bar, so there are 20 pieces. And to use this formula, all we have to do is to mark the 20 pieces and each one's center. So this one right here has a center, and let's call this position x1. And it has mass, so we'll call it m1. And this m1 is 1/20th of the total mass. And here we have x2, right? x2, and that's mass m2. Apparently the masses are the same, although the positions are different, right? Starting from 0, so this is 1/20th, actually 1/40th of 0.5 meters. So 0.025, 0.0125. So let's not worry about the exact position. We're just trying to make use of the point mass formula by approximating this into a number of point masses. So we have all these centers, right? So this just keeps going, and we have x19, x20. So here we have m19, and let's get rid of that. m20. So we'll put this 0.5 here. Alright, so what we have is a sum, right? It's a summation of all these small pieces that are, well, not exactly point masses, but we will have to do with that. So this is what we're going to do. We're going to have 20 terms on the top, 20 terms on the bottom. And as I said, this is not very good approximation because the sizes are not very small. Okay, so how do we deal with that? Well, we can subdivide each piece into smaller pieces, such as this one here. I haven't given a name yet. So if I could divide it maybe in half, maybe even in 4 separate pieces. Let me do a little better job dividing it. Okay, so here's half. Okay, here's approximately a quarter. Okay, so the size of each piece is now smaller, quite a bit smaller. And if I have another one that's somewhere over here, I just randomly picked this. Okay, so their distance is quite a bit bigger than their sizes now, right? So now we have a recipe to actually use this literally, accurately, is to subdivide each piece into smaller pieces, and even smaller pieces. Okay, so what does that do to our formula? We had 20 terms here, so if we subdivide each piece into 4 pieces, so now we'll have 80 pieces, and the numbers will just go up, and maybe there's 4 pieces, 4, 4, 4, right? So just keep going, and we'll have an 80 piece. Basically, all of these pieces will go into the top and the bottom, right? Mass times the coordinate. And that's one outcome. We have more terms. Another outcome is we have less mass per term or per piece. So a piece like this will have this much mass, and a piece like this will just have a quarter of that mass. So as we shrink the size of each piece, the mass shrinks proportionally, but the coordinates are just about increasing more and more, well, I would say smoothly. So with the 20 piece situation, we just jump from this coordinate to this, right? There's this 1/20th of a total length. So from the 80 piece, we go from, say, from here, the center, to this center, and that distance only a quarter of this. So there will be more pieces, more coordinates mentioned, and the coordinates will differ by less and less amounts, right? So if we do a limit of that, such as let's just do the bottom piece here, we're summing the masses, right? So let's still sum the mass, and we'll skip the iterator and limits. So we'll sum the mass, and we have a limit. We'll have a limit where the delta x, which is the size of each piece, approaching 0. Okay, so approaching 0, and what happens is we'll have an integration of a dm. So the dm is a very small amount of mass. Well, how small is it? Well, it's infinitesimally small. So whatever finite size mass you can find is too big. This is infinitesimally small. And we'll also have the same exact limit, delta x approaching 0, for the other sum, so mixi. So mi becomes dm, but xi doesn't change into dx because x is just a coordinate, the location of each piece. It doesn't go to infinitesimally small. It has to run from 0 to 0.5. So m becomes dm, and xi just x because it becomes continuous as you get finer and finer cuts. So x dm. And we can also specify, because we were missing these limits, right? We didn't really know where to start, where to end. Well, that really depends on how many pieces we're cutting. Say we cut the bar into n pieces. So here I equals 1 through n. Alright, so equivalently, we're going from a coordinate 0 to a coordinate 0.5. So this is equivalent to x equals to 0 to x equals to 0.5. And here the same thing, x equals 0 to x equals to 0.5. Alright, so if you have learned integral calculus, well, you might know this integration cannot be calculated because Well, this dummy variable is m, and there's this x, and how is x and m related, right? And also the limits are specified not with a dummy variable, but with this x. So something has to be done in order to make this integration even doable. So if you haven't done any integral calculus, that's fine. So let's just imagine what is a dm. We cannot draw infinitesimally small masses, but we can pick a small finite size just to make a point. So let's still pick this dm right here. So here, here's a small mass. I can call this delta m, still finite. Okay, so how much mass did I just include? Well, because we have a uniform density, so the mass is actually proportional to the width. So the delta m here is delta x, the width of such a piece, times the lambda, the density. Lambda is the linear density, or lambda delta x. Okay, so that's how much mass is included. And if we go through the limit of squeezing the delta x into 0, and then this will change into the delta x into dx, right? Lambda dx. I like to keep the dx on the right side by convention. So now we know how this is going to change. This is actually going to replace that dm. Okay, so in this equation, dm cannot be integrated now. In this equation, you can replace dm with dx, and now you also have this x you can actually integrate, which means to find what is the antiderivative of x. Okay, that's probably 1/2 x squared, right? So now you can integrate. So it is critical that you do this. You turn this dm that is pretty much useless into this expression that is useful. So turning this dm into a coordinate related variable. And without that, we cannot really integrate at all. So now that we know this is just a review on the left side. So dm turns to lambda dx. Then x dm will just turn into x lambda dx. And if the lambda is a constant, then this constant passes through the integration sign, so it gets pulled out. If the lambda is not a constant, say you have a variable density bar, and then the lambda will stay inside as part of the integrand. Okay, so back to the uniform density example. So how are we going to do this? We'll do the top integration, and then we'll do the bottom integration. The bottom integration is supposed to give us what? The total mass, right? Total mass 0.6 kilograms because of the length and also the density. So let's do the top. So xdm is equal to, let's specify x equals 0, x equals 0.5, and x, the dm is lambda dx, and lambda is a constant 1.2. So let's pull lambda out, and then we'll have x dx. Because the dummy variable is already x, we can skip the x equals, just specify the values, assuming these are for x values. So we're asking what is the antiderivative of x, that is x squared over 2 to x squared over 2, and we need to evaluate this expression at 0 and at 0.5, right? So the result is lambda, I like to keep it here, so x equal to 0.5 and x equal to 0. Okay, so this is going to be a 0, and let's start a new line. So now we have lambda is 1.2 times 0.5 squared and divide by 2. That's a quarter, then divide by and another 2 is 1/8. So 0.125. And you can just do this, eyeball it, or you can use your calculator. Just pause the video and use your calculator. So this divided by 8 is 0.6, 0.3, 0.15. Okay, so that's 115. And now let's move on to the next part, which is finding the total mass. This is pretty obvious. Total mass is 0.6 kilograms, but let's find it anyway. So dm, and we'll convert the dm into the lambda dx, and we know we start from 0, we end at 0.5. Lambda is constant, pull it out. So now we have just 1 dx. Okay, so we're asking the question, after differentiation, something turns into a 1. Okay, so what is that function? That must be an x, so lambda x. And we evaluate at 0 and also at 0.5. So this gives us lambda and 0.5 minus 0. So that is 1.2 times 0.5, which is 0.6. It's kilograms, right? So now we have both the top and bottom, we just divide the two. So x center mass is equal to the top, which is x dm, and bottom is just dm. I'm going to grab a ruler, draw a nice horizontal line. So we have 0.15 over 0.6. And we should have 0.25. And I'll put the unit here. So this is exactly halfway, right? 0.25 right here. So let's review this. First, we have this bar here, and it sits between 0 and 0.5. And then we need to find out the center mass. The center mass has two integrations, xdm and dm. And in order to integrate, we need to turn dm into something that can be integrated with dx. So this is a formula right here. dm is lambda dx. This is in one-dimensional situation where you have a bar. Right? So dm is lambda dx. So anywhere you see dm, you turn into lambda dx. So this turns into x times lambda dx, and that turns into lambda dx. And now it doesn't really matter if the density is uniform or not. You just replace lambda with whatever expression you have, either a constant or you have an expression that is related to x. So we did the integration, and x turns into x squared over 2, and you plug in these values and you evaluate. That is this is a numerator, and the denominator gets you the total mass. So that is integrating 1 dx, so you get x, and then you can evaluate that total mass, then do a proportion. So this is your final answer in center mass. Thanks.